Hello! In this session, we will introduce to you the different ways that you can connect to big data using Spotfire. Tibco Analytics provides different ways for you to access your data and to tailor your application to your environment and your needs. By the end of this session, you will have understood all aspects of this image. I will also be demoing in Spotfire. Spotfire can connect to different types of data stores with our certified connectors, including SAP HANA and BW, Oracle, Cloudera, Spark, etc. You can obviously also load Excel or text files if that is what you're interested in. Spotfire adapts to either. As you can see in this diagram, there are two main ways of getting value from your data: visualize it and run calculations. Let us start with visualizing big data. In Spotfire, there are three ways of connecting your visualizations to your data: in memory, on demand, and in data source, and the ability to combine them in any way you want. In memory is as fast as it gets. Spotfire can handle up to 1 billion rows. On demand loads data smartly. You only load data when needed and what's needed. In data source, sends live queries to your data source, so there are no size limits, basically. Not only is your data access very flexible with Spotfire, but you can also visualize big data hyper fast. For example, using in-data source, I have seen Spotfire querying 834 million rows of data over 12 Hadoop nodes and the visualizations responding in half a second, next to instantaneously. I will demo the different strategies of visualization later, but let me first explain how to run calculations on big data. Getting back to our diagram, we are now in the Calculate section. There are two main approaches to running your calculations: using embedded TERR when the data is in memory, or using shared server resources. We shall start by explaining embedded TERR. TERR, or Tibco R, is an interpreter created by Tibco for open source R that turns R from academic to enterprise quality. TERR has better memory management, is faster and more robust. It can handle bigger quantities of data and is fully supported by Tibco, and it is free from R's GPL license issues. TERR comes with on-premise Spotfire, meaning that when you buy Spotfire, TERR is already in it, no need for extra installations. You can use it for running any sorts of calculations on in-memory and on-demand data. For example, you can load total sales over time from your big data, load it into Spotfire, and then use embedded TERR for forecasting future sales. However, if you want to do calculations on in-database data, you will need to use TERR on a server, which brings us to the next section. Let us explain our server resources. Spotfire can call calculations to be run on shared resources using TSSS. TSSS stands for Tibco's Spotfire Statistics Services and is a gateway that Spotfire uses to connect to a number of statistics engines, or even to call calculations on distributed clusters such as Hadoop. Because we want you to leverage your current analytics resources on our platform, with TSSS, Spotfire can call calculations to be run not just in TERR, but also in SAS, MATLAB, open source R, or other engines. Furthermore, you can connect Spotfire to NIME and LavaStorm, which are workflow tools. Of course, TERR is our engine of choice. Let me share a few more things about TERR via TSSS. By default, TERR, as well as R, is single core and single node. But it is important to be aware that TERR via TSSS can be set up as a single large machine or as a cluster of parallel machines. When we use TERR parallel package, we can transform TERR into a multi-core system, and we allow it to use any number of available cores on your machine, which maximizes the usage of computation resources. Besides using multi-cores on one machine, you can also expand your computation capacity by using more machines. This is called multi-node. When TSSS has been set up as a cluster, we have a multi-node TERR installation. TSSS as a cluster includes a weight balancer to ensure a fair distribution of computational workload between the nodes. If you require more information, please consult the TSSS installation manual via this documentation link, which is also on our Tibco community and on the Spotfire website. As the final part of this diagram, let me explain the two main approaches for calculating with data that remains in data source. This is big data that is just too big to fit on your computer. How can we run calculations on this data? Well, there are two approaches. The choice between these approaches depends on the flexibility of your data source. If you are using non-SQL type of data sources like Hadoop, Spark, Netezza, Teradata, or Vertica, then you can use the engine-to-data approach. Wherever possible, it is the best strategy to use. In the engine-to-data approach, we install the statistical engines on the same distributed computers as where the data lives. This means that the data does not need to travel, which is more efficient, naturally. Some SQL databases also allow R to be run directly in the data source nodes. In principle, where R goes, TERR can also go, and so for them too, you can use an engine-to-data approach. But typically, if you are using a standard SQL database, like Microsoft SQL, SAP, Oracle, or IBM, you must use the data-to-engine approach. With the data-to-engine approach, you load big data from the data source straight to your statistical engine on the server. Starting with the preferred engine-to-data approach that runs on NoSQL type of data sources. NoSQL data sources like Hadoop are distributed over several computers, which makes data storage quite inexpensive and limitless. For running calculations on distributed data sources, we just put TERR in each of those computers. We can then just reach out to TERR and Java engines in them for our calculations. They will run any form of distributed parallel and therefore efficient calculations. The calculation results are later visualized in Spotfire. So let me demo the engine-to-data approach. We will also demo the 3 different ways of connecting to data, and we will show embedded TERR. In this demo, we show fictitious data for a wholesale company distributing merchandise to retailers. We have several distribution centers or sites in 3 countries. They have noticed that a proportion of their shipments goes missing. Their goal is to identify the problematic shipments in order to investigate them for fraud. The company has a large data set of transactional data over 3 Cloudera Hadoop nodes. I will start by demoing in-memory capabilities. On the first page of this demo, we see a sample of 100,000 records that have been uploaded into memory. We start with some simple data exploration. On the top here, I have a histogram of missed volumes. Below, I have a scatter plot where each point is a shipment and the axes show the volumes that were shipped against the volumes that were missed. Because the data is in memory, I can use embedded TERR to cluster these points. Clustering groups of shipments that have similar levels of lost and shipped volumes. As part of the data discovery process, I can change the number of generated clusters, which I can do using this slider. If I change the value on the slider, my visualization responds automatically. So what is happening in the background? Well, if I hover on cluster and go into the custom expression, I can see that the expression TERR integer, which is one of the ways Spotfire calls embedded TERR directly onto a visualization, is being used to apply TERR's k-means clustering method on the data. The n on this expression is fed by a document property called n, which is associated with the slider. Apart from TERR integer, Spotfire also provides 256 calculations options. For example, the 10th percentile and the 90th percentile of a variable. Another great feature of Spotfire is that you can augment the list of available calculations with your own calculations. In this example, I created my own cluster expression, as you can see in the description where it says Ana's doing. The cluster expression was defined using TERR, but now everyone can apply it without knowing how to write TERR. This great benefit also applies to data functions. Data functions allow running any script in any language, for example SAS, MATLAB, and of course TERR, that can then be called from Spotfire by your non-script writing users. This page now shows another example of calculations that you can do with embedded TERR on in-memory data. We have a time series with the total volume shipped and the percentage of that volume that went missing in action. When I right-click and press Forecast, local TERR predicts the future values of these time series using the inbuilt Holt-Winters algorithm. So in this new sheet, I will display how we work with data on demand. When working with data on demand, Spotfire gathers information from the data source about chunks of data at a time. In this example, we have configured on demand to allow the user to retrieve information about up to 3 different distribution centers at a time, so as to guarantee performance. The visualizations update accordingly. When the user finishes analyzing these 3 sites, he can choose another set of 3 sites, up to 3 sites. Spotfire discards the data on the old sites and gathers data for the new sites. Now I will demo the third option in data source. The data stays in the data source and only the few numbers necessary to populate these visualizations are reported into Spotfire. In the background, as I play with the visualizations, Spotfire generates the SQL that it interrogates the data source with. In this example, the visualizations show an analysis of sales which responds to my choices of countries. Because the data is in database, you must use SQL calculations that are available in that data source. If I look at the list of available expressions, I can see that they are not the same as Spotfire expressions I was using before in memory data. For example, TERR_integer is not there anymore. Instead, the list automatically reflects Cloudera Impala recognized expressions. For example, sum is now the sum as Cloudera defines it, which means that you can use the familiar Spotfire interface to run in-database expressions. And this is available not just for Cloudera, but for any other data source that Spotfire connects to. Another important feature here is that the last value responds to a document property that the user can select with this slider. This is very useful, for example, if we want to make what-if sensitivity analysis on in-database data in Hadoop or other big data stores. We have so far then demoed the 3 different ways that you can power your visualizations: in memory, on demand, and in data source, that allow you great flexibility when you combine them to answer your business questions. But back to our use case of finding problematic shipments in order to investigate them. One way to do this is to use a regression model to explain the behavior of missed volumes in every combination of country customer. We want now to use all the data that we have available, so we must do our calculations in Hadoop. As we said before, Hadoop data is distributed over many computers or nodes, so we put TERR on each of those computers for running our calculations. We will develop our models separately in each of the TERR engines. The different TERR engines then work on their chunks of data on their own computers in parallel and simultaneously and send the result back into Spotfire. This is, in Hadoop jargon, what we call MapReduce. On top of this page, the table in black has the name of all the columns that are available in our data. In the blue table, the user tells Hadoop how to organize data in the Hadoop computers. In our example, we want to organize it by customer and country. In the orange table, I choose which variables I want to use in my model. I choose missed volume as the variable we want to explain, and shipped value and shipped volume as the variables I want to explain missed volume with. Below, the user can choose which of the available calculations he wants to do. He could, for example, choose sales forecast. In my case, I want to run a regression model. Now, when I press the button, Spotfire takes my choices made on these two parts of the page, passes them via TSSS to the remote TERR. Remote TERR compiles them and passes them to Hadoop using the system command. Hadoop itself then manages the TERR on each of the nodes to run the calculations in parallel. Business users, as experts on the business process and the meaning of the data fields, can use this interface after some initial basic training without requiring technical support. In this other page, we have a similar interface targeting data scientists and analysts who can write TERR. In this page, we add a display of the code that we can use as an interface for them to create new or change existing codes to be run directly in the Hadoop nodes. This then illustrates another of the Spotfire strengths. Spotfire serves as an interface that is familiar for even more advanced users to run and specify calculations without needing to be concerned with where the data lives and the nuts and bolts of the Hadoop environment. Okay, now MapReduced has finished running. The results of the calculations get stored back in Hadoop and are visualized in database in the results pages. They could also have been sent directly into Spotfire. This page should be read clockwise. At the top, we show the shape of the models that we created. We will be explaining missed volume as a regression of shipped volume and shipped. We made as many models as there are customer country combinations. The result of the calculations are the values in green: intercept, coefficient 1 and coefficient 2. We will have as many of these three results as there are clients and countries combinations in our data. 36,000. If a customer country shows an unusually high coefficient 1, it means that shipments to this customer in this country have a bigger chance of getting lost when shipping volumes are high. A high coefficient 2 means the shipments to this customer in this country have a bigger chance of getting lost when the shipment has high value. Finally, a high intercept means that shipments to this customer in this country are more likely to get lost, regardless of which volumes and values are being shipped. So now, on the right-hand side, I can choose the country customer combinations that display unusual values in any of these three coefficients. When I select them on the chart, their details appear on the left-hand side. This is a good place for me to start my investigations. We should investigate n country clients. Assuming each one takes 2 hours to investigate, below we can see the number of man-hours that is involved as an effort. This knowledge helps us manage resources. So this is all very useful already. But what if I want to run a single model on all my data at once rather than by customer and country? In order to obtain a model from a distributed environment like Hadoop, to obtain one single model, we can, for example, use TERR to run models separately in each of the nodes and then combine them using ensemble techniques. Another option is to use Spark MLlib if you are working with Spark. Or you can use H2O, which is what I will demo in this page. H2O uses Java to do calculations in parallel in the nodes and get the nodes to communicate just enough to obtain a single model that covers all the data. You can call both Spark MLlib and H2O from TERR. On this page, the user can select at the top the variable that he wants to predict and the variables that he will use as predictors. He can then choose the type of models he wants to run in this list of available H2O models. On the surface, these steps are similar to the MapReduce example. However, we do not start by organizing the data in the nodes, as H2O uses all the data at once. We had previously run the random forest on all the data. All the available outcomes of the H2O model are displayed in the text above, which is useful for data scientists. Below, we show a chart with a variable importance. Variables at the bottom are less important in terms of their ability to predict shipped values, so we may consider ignoring them. Let us now try a different model. I choose GLM, which is, again, a regression model. I press Fit Model, 1, 2, 3, and there's my results. A lot of variables in this case are not considered relevant for GLM. Let us now exclude them and run the model again. 1, 2, 3, voila! On top of 1 million rows of data, H2O took 3 seconds to run and deliver us a result into Spotfire. The final sheet in our demo shows the result of applying H2O model on a set of 100,000 shipments that we sampled so as to use for testing. So they were not used for making the model, just for testing. At the top, we have a histogram of the prediction errors trellised by country. We can see average error is 0 in all countries. Below, we see a histogram of the actual predictions. Shipments where missed volume is higher appear on the right of the histogram naturally. We color the bars of the histogram in darker blue when the actual average missed volume was higher. Darker blue shades appear in the right side of the histogram, which means that we get higher predicted volumes when missed volumes were actually higher, which gives us confidence in the quality of the model. If I now want to use this model to identify shipments that I want to investigate in real time, I just have to press this button. Spotfire and Tibco event processing technology communicate very efficiently. The number of shipments that I want to investigate is a business decision that depends on a threshold of tolerance. The histogram informs that decision. I can just select the threshold directly on the histogram, press the button, and send it also to Tibco real-time engines for evaluation. Another engine-to-data example is Spark, and these days we cannot talk about big data without mentioning Spark. Spotfire uses the Spark SQL connector to connect to Spark in database. You can then use TERR to power your Spark R jobs directly in the Spark cluster, and this will bring you the extra speed of execution that TERR has in relation to R. Spotfire can also be used as an easy-to-use interface for Spark R. So just like we showed in this Cloudera example, how we can use Spotfire to run and create and edit TERR jobs, you can do the same to run, create, and edit Spark R jobs from the Spotfire familiar environment, which makes life easier for data scientists. Spark MLlib models can also be called from Spotfire, and we can also combine Spark with H2O, and this is called sparkling water, so as to run H2O models on the Spark environment, and we can call these from Spotfire again. Finally, I will explain the data-to-engine approach. With this approach, you load big data from the data source directly to your statistical engine on the server. TERR can do this either by reusing the same data source access that Spotfire has, using the TERR Spotfire data package, or by connecting straight to the data source using the R's SJDBC package. So let us go into more detail. Spotfire holds information about in-data source tables in a Spotfire connection. This connection is stored in the Spotfire library. The Spotfire library is shared by all Spotfire users. In this example, our connection is called Connection Both. Inside Connection Both can be not just full tables, but also custom queries. Custom queries can receive any select SQL statements, including, since 7.5, nested queries. Nested queries are great because they allow combining detailed transactional data with aggregated data into one same table. In this example, the connection holds access to a table called demodata.ana_table. And the connection also holds an SQL view, which is called query. This query receives a parameter called text content. Spotfire gets the value for this parameter via document property or by prompting the user directly. The latter, prompting, is nice because it allows a simple way for the user to dynamically subset the data that they are accessing. Now, TERR can reuse all this information. We will show a piece of TERR code that you can use to do this. You can put this TERR code into a Spotfire data function. In this code, we use the Spotfire data package to connect to the Spotfire library, open connection both, get the data from the view called query, and supply the text content parameter that the view requires, which TERR receives from Spotfire as a document property. And that's it. The data that we saw in Spotfire gets loaded into TERR. Now, we said there were two options, so you can also use R's SJDBC package. If you use that, then TERR will ignore the metadata for the Spotfire information connection. This means you now have to supply that information again. This approach requires TERR to have a data source driver. This can be obtained from the data source website itself. The driver must be stored in the TERR location and that is specified here in this file path and called again in the script. In this example, we are importing, using the import JDBC command, we are importing the demodata.ana_table. We must supply the data sources connection, address, user, and password. Instead of having the whole table, we can also get data from a specific query, SQL query, including, of course, nested queries. Finally, the export SJDBC function allows us to export the result of our analyses straight into the data source itself, and this can be useful for many use cases. So, in conclusion, with Spotfire, the business end user has ease of use, but at the same time, below the surface, you have the versatility and power that combining TERR and Spotfire allows. In summary, with Spotfire, any end user can have an easy-to-use interface for visualizing big data, launching all calculations, analyzing results, and deploying results in real time, whether it's on big or small data. We have seen the various ways of visualizing and running calculations on big data from Spotfire, and how Spotfire provides easy-to-use interfaces that meet the needs of all types of users, from data scientists to business. I do hope you found this information to be useful, and thank you for joining.